So let's look at the first question over here. So this question, we are going to change the magnetic field strength, and that will cause a change of magnetic flux, and that will induce an EMF. Okay, so a coil of 30 turns, an area of 0.025 meter per second, meter square, sorry, 0.025 meter square, is in a uniform magnetic field of 0.042 Tesla. Okay, the magnetic field is perpendicular to the coil. So if you see my diagram over here, the situation we are given with, we have a coil with 30 turns, and the area is 0.025 meters squared, and it is in a uniform magnetic field, and the uniform magnetic field has 0.042 Tesla. Okay, the magnetic field is perpendicular to the coil, so it can be either pointing into the page in this diagram, or it can be pointing out of the page in this diagram. So for me, I pick pointing into the page because it's easier to draw, it's clearer to see. Okay, next, calculate the induced EMF in each of the following situations. First is when the magnetic field increases to 0.075 Tesla in 20 milliseconds. So it means by through the duration of 20 milliseconds, your magnetic field increases from 0.042 Tesla to 0.075 Tesla. That is what happened over here. You're going to change your magnetic field from 0.042 Tesla to 0.075 Tesla, and it all happens within 20 milliseconds. Okay, so this time they tell clearly is increasing or decreasing right now. If you look at the previous question up there, they just say the rate of change, or just say whether it's changing, but they never define whether it's increasing or decreasing. So right now, this will be slightly more specific than the question earlier. They are telling you whether it's increasing or decreasing. Okay, so we are going to use Faraday's law as usual. Then Faraday's law is only this equation, but we are going to modify we are going to derive the equation in a way that allow us to insert the change of magnetic field into the equation. Okay, so the Faraday's law tells us that epsilon, the induced EMF, is equals to the negative of the phi, big phi, the magnetic flux linkage over dt. And we know that phi, this magnetic flux linkage here, it's N multiplied by small phi, which is BA cos theta. So we expand the magnetic flux linkage to become MBA cos theta. This is what we do right now. Then after that, what do? We take out everything that is constant out from the differentiation bracket. So this is changing with time, right? Because there's dt below. So what we do, we check whether all these things is changing with time or not. If it's not changing with time, we are going to bring it out from the differentiation bracket. So the first thing to check, the number of coils. So initially, the number of coils is 30. Final, the number of coils is 30. So the number of coils, number of turns never change. Therefore, you can bring the N out from the differentiation bracket. Okay, next thing, the magnetic field. If you look at the magnetic field, you see that the magnetic field initial and the magnetic field final indeed does change. It is increasing. Therefore, this is changing with time. You have to keep it inside the differentiation bracket. Okay, continue. The area over here, initially the area is 0.025 meters squared. Final, the area is also 0.025 meters squared. So the area never changed. So the area is constant with time. We can bring it out from the differentiation bracket. And lastly, theta. Theta is the angle between the magnetic field and the area vector. So in this situation here, we need to pick our area vector. If we set the magnetic field to be pointing into the page, then our area vector, is good that we pick it to follow the direction of the magnetic field. It must be perpendicular. So in this case, perpendicular is either pointing out of the page or pointing into the page. We want it to be more convenient by picking it in the same direction of the magnetic field. Therefore, I pick it to be into the page. So therefore, I draw my area vector to be pointing into the page. Okay, before and final, I never rotate my coil. So my area vector is still pointing in the same direction. Before and after, it's still pointing in the same direction. My magnetic field is also pointing in the same direction. So the angle between the magnetic field and the area vector never change. Because B and A, they are both pointing into the page. before, final, both pointing into the page. Therefore, the angle between B and A never change. It's constant with time, so we can bring it up. Can bring it up. Okay. So what's left in the differentiation is only the magnetic field. And now dB dt, it's now it carries the meaning of rate of change of the magnetic field, or rate of change of the magnetic field strength, or rate of change of the magnetic flux density. Okay, so right now you enter this stage already, you are almost done already. Okay, if you look at the situation you are being given here, they tell you the initial situation, they tell you the final situation, and they tell you how much time it takes to finish that situation. So they are not straightaway telling you that it is increasing at a rate of 0.5 Tesla per second. They are not saying things like that. They're telling you the initial and the final situation. So how does it get from initial situation to the final situation? Whether it increase constantly or increase fast, then increase slowly, that one is beyond our knowledge. So because we don't know what happens in between, we can only get the average. Okay, it's similar to what you learned in kinematics of linear motion last semester. Okay, you learn that if you know the initial velocity and the final velocity, but you don't know how it gets from initial to final, you can only find the average acceleration. Okay, or you know the initial position, you know the final position, but you don't know how it moved from initial to final, then you can only find the average velocity. You cannot find the instantaneous velocity. So you know the initial and final situation, you don't know how does it change from initial to final, you just know it increases. So because of that, you cannot use dB/dt. You have to change dB/dt to become change of magnetic field divided by change of time. So now you can substitute up and down separately. If you keep it as dB/dt, dB/dt you can only sub in a value. dB/dt is the rate of change of the magnetic field. We can only sub in a value. Okay, like how much Tesla per second. But now if you change it to become delta B over delta D, delta T, you can sub in delta B as one value, you can sub in delta T as one value. You can separate the substitution. But now you have to change it to become average induced EMF when you do this change over here. Okay, so everything is still very clear cut. Now it's just substitution. Negative, the number of turns is 30, the area is 0.025, the angle between the magnetic field and the area vector, they are both pointing into the page. So the angle between them will be 0 because they're in the same direction. So change of B, you take final minus initial. Change is always final minus initial. So you take 0.075 minus 0.042. That is a change of magnetic field. And the change of time, which is the duration is just 20 milliseconds. So substitute in 20 milliseconds. And from this calculation, we see that the average induced EMF is negative 1.24 volt. So this time, the negative here, is it important or not? Yes, it's important. Why? Because they tell you clearly this is increasing magnetic field. They are not just saying it's changing magnetic field. It's increasing. So they clearly tell you how the magnetic flux will change. The magnetic flux will increase because of the increase of magnetic field. So because everything is defined very clearly right now, so the negative here carries a meaning. It carries the direction of the EMF. So the sign here is indicating the direction of the EMF. So how do we determine the direction of the EMF? Is by using right hand rule. You learn this point fingers and curl thing, right? That's right hand rule. Again, it's only right hand. I never use left hand in my class. Okay, so if you get a positive answer, what you need to do is you need to point your thumb in the direction of the area vector, then the fingers will curl around the direction of the EMF. So if you get a positive answer, then you will point your thumb into the page, then you curl around the page, then you see that your fingers should be curling around clockwise. Again, this is your board. This is your board. You put your fingers, thumb, point like this. Okay, this is your board. The thumb pointing into the page. Then your fingers curl like this. And you see that your induced EMF will be in clockwise direction. Okay, point like this. So it's in clockwise direction for your induced EMF if your answer is positive. But if your answer is negative, which is our case right now, then it's opposite of what I determine if it's positive. So positive, we determine it to be clockwise. So negative means by its opposite direction, anti-clockwise. So that means by in this diagram over here, our induced EMF is happening in an anti-clockwise direction. So your induced EMF is happening in an anti-clockwise direction, and that will cause your induced current to flow in the anti-clockwise direction. Okay, this is how you determine the direction of the induced EMF and the direction of the induced current. So through this increment of magnetic field, it will create an induced EMF in the anti-clockwise direction, causing current to flow in the anti-clockwise direction. That is what happened within this 20 milliseconds. Okay, but as you remember just now, I defined the magnetic field to be pointing into the page by myself. It is not decided by the question over here. The question never say the magnetic field is pointing out of the page. It just say that it's perpendicular to the coil. So if you take your magnetic field to be pointing out of the page, if you change all this to dot, then you pick your area vector to be pointing out of the page as well. Okay, if you pick your magnetic field to be all pointing out of the page, and your area vector will be pointing out of the page, then in that case, your hand will be curling anti-clockwise for positive, so negative will become clockwise. Then your induced EMF or your induced current will be in clockwise direction if the magnetic field is pointing out of the page. Okay, the induced current and the induced EMF are both pointing clockwise if the magnetic field is pointing out of the page. Okay, so it depends on the diagram that we draw. In this case, we draw a diagram to be pointing into the page. Therefore, the magnetic field, therefore the induced EMF and the induced current is pointing anti-clockwise. Okay, so this is how you solve the problem over here. Again, it starts from the same equation, the Faraday's law. Okay, look at the next question. Now, if the magnetic field decreases from 0.042 Tesla to 0.036 Tesla in 30 milliseconds. So now the initial situation, we have a magnetic field of 0.042 Tesla. The final situation, we have a magnetic field of 0.036 Tesla. The others don't change. The number of turns remain at 30 turns. The area of the loop over here is also 0.025 meters square. Nothing much has changed. Only the magnetic field has changed. So the steps to do this question is still the same. You break the magnetic flux linkage over here to become MBA cos theta. You take out what is constant. The number of turns is constant. The area is constant. The angle between the B and the A is constant. You bring it out. Again, we are going to take the area vector to be pointing in the same direction as the magnetic field. Okay, I mean on the same side as the magnetic field. So in this case, the area vector will be pointing into the page. So right now, we are going to change this dB dt here to become delta B over delta T. Now only you can substitute the numerator and the denominator separately. If it's dB dt, you submit one single value to represent dB dt. And it's the gradient of the dB of the BT graph. Okay, so you substitute in N30, A 0.025, angle between the magnetic field and the area vector is still 0 degree because they are pointing in the same direction. But for now, the change of magnetic field, you take 0.036 minus 0.042. So now it's a smaller number minus a larger number. So you should expect the numerator here to be a negative value. Because it's small minus large, you get a negative value. Divide by the time, 30 milliseconds. So this bracket here has a negative. Multiply with a negative in front. Therefore, you get a positive answer of 0.15 volt. So right now, the answer is positive 0.15 volt. That means that if you use your board to determine the direction of the magnetic field, the direction of the induced EMF, the area vector is pointing into the page, so our thumb is also pointing into the page. So if you curl things around, the curling will be in clockwise direction. Okay, and since positive is our answer, so this is what we determine here is the induced EMF. You do need to flip the direction. Okay, so right now the induced EMF and the induced current are both happening in clockwise direction. Okay, so now you see that if the magnetic field decrease, then the induced EMF and the induced current is in anti-clockwise direction. But if the magnetic field decreases, then the induced EMF and the induced current is in clockwise direction. So how does the magnetic field change will affect how the magnetic flux change, and how the magnetic flux change will change the direction and the value of our induced EMF and induced current. Okay, so it's important to see whether it's increase or decrease. If they do tell whether it's increase or decrease, technically the sign of our answer doesn't carry any meaning anymore, because we don't know whether it's an increment or a decrement of the magnetic flux. Then the answer for our induced EMF will carry, the sign of the answer of our induced EMF will not carry any meaning anymore. Okay, so this is question B. We are going to skip question C because it's the same thing. It's just changing another value, changing another time. We are going to skip D because D is on angle, changing the angle. That one we'll discuss it later. So let's move on to question E, which is the magnetic field changes at the rate of 0.64 T Tesla per second. So right now they tell you that the dB/dt here is equals to 0.64 Tesla per second. But again, you see the keyword, they use changes. They are not saying that it's increasing at the rate of 0.64 Tesla per second. They are not saying it's decreasing at the rate of 0.64 Tesla per second. So whether this is an increase of the magnetic field or decrease of the magnetic field, we can't determine for sure. So that means by this value here, right, we don't know whether it's positive or we don't know whether it's negative. We don't know. So later when we get our induced EMF, whether it's positive sign or negative sign, the sign doesn't carry much meaning anymore, because you don't know whether it's an increment or a decrement of magnetic field right now. Okay, so let's move on to question E. So right now they say that the magnetic field changes at a rate of 0.64 Tesla per second. So that means that we don't know the final situation. We just know that in the process of these 30 milliseconds over here, do they even tell 30 milliseconds? No, they don't tell the time. So there's no time over here. I should remove it. They just tell you as time goes by, the magnetic field will change at this rate over here, 0.64 Tesla per second. So it's not an initial and final situation anymore. They just tell that in between. So as time passes, this is how the magnetic field will change. For every second that has passed, the magnetic field will change by 0.64 Tesla. Whether it's increased by 0.64 Tesla per second or decreased by 0.64 Tesla per second, we don't know. Okay, but for this kind of question, we don't need to change it to delta B over delta T, because we are not comparing between final and initial right now. It just tells us that it's changing like this. So if that's the case, you don't need to change it to delta B over delta T. When you reach this stage, you can straight away substitute the N, the A, the cos theta is still 0, and the dB/dt, you can just substitute 0.64. But we are not sure whether it's increasing or decreasing. So even though you get the answer to be negative 0.48 volt, then there's a sign negative here. But all these signs here are meaningless if you're not sure whether the magnetic flux is increasing or decreasing. So even though you have a negative sign here, the negative sign here is not telling you the direction. Because it can be you substitute in negative 0.64 over here. Let's say it's decreasing at a rate of 0.64 Tesla per second. Then you can put in negative 0.64, then you get positive 0.48 also. So you don't know whether it's negative or positive, so the sign here doesn't carry much meaning anymore. Okay, technically what are you determining here is the magnitude of the induced EMF, the absolute value of the induced EMF, or whether this induced EMF is in the clockwise direction or anti-clockwise direction can't be determined anymore. Okay, so this is how we solve a question involving change of magnetic field strength to change the magnetic flux.